Hello again. Moving on to 7.2, trigonometric integrals. Again, so let's review a couple of identities from pre-calculus, actually. So one identity that we need to remember is that sine squared x can be replaced by 1 minus cosine twice x divided by 2. Of course, similarly, cosine squared x is 1 plus, the same thing, but plus cosine twice x divided by 2. Now, this is a dynamic. They are dynamic in the sense that if this is, let's say, 4x, this will be multiplied by 2. So this will be 8x, and so on and so forth. If this happens to be 3x, obviously this will be 6x, and so on and so forth. The other trig identity that I would like us to review quickly is the most important one, the Pythagorean identity, which is sine squared x plus cosine squared x equals 1. From here, we have two other identities that are extremely important. If you divide both sides term by term by sine squared, you get 1 plus cotangent squared equals cosecant squared. If you divide both sides by cosine squared, then you get tangent plus 1 equals secant squared. So these two identities come from the main one. Again, how did I determine the first one? I divided both sides by cosine squared x, and I got this. And then I divided the same identity, the Pythagorean identity, by sine squared x. It's the opposite, sorry. So when we divide by sine squared, we get this. And we divide by cosine squared, we get this. Tangent plus cosine squared over cosine squared is 1 equals 1 over secant squared. So please remember these three, basically 1, 2, 3, 4, or 1, 2, 3, 4, 5. All these identities are extremely important. Okay, so this section is divided basically in, I would say, two parts. Part one, when we look at powers of sine or cosine. So integrals using powers of sine and cosines. Fine. So what happens here is if sine has odd power, use the other notation. Denote u by cosine. If cosine has odd power, use the notation u equals the opposite. If sine plus cosine, both, I would say maybe and, cosine have even powers, that's when these two identities come into play. Use sine squared and cosine squared, maybe to simplify, maybe to reduce powers, etc. We'll see. So let's take a look at a few examples. So I like to start with number 1. And number 1 is on page 498. And we have the integral from sine to the third cosine squared, yes. Okay, so as we mentioned, as a general rule, if sine has odd power, and it does, then we denote cosine by u, or any letter, it doesn't matter, it doesn't have to be u. So u equals cosine x. Of course, du equals negative sine x dx. So I have to borrow a sine and dx, and I'm missing a negative sign. That's not a big deal, as we discussed. I multiplied twice by -1, and there is no change there. So let's move on. I'm on page 2. Let's take a look. So then from here, I'm going to jump here, and let's see what we get. A negative stays outside. The negative, one sign, and dx will be replaced by du. But I have a sine squared left over. But sine squared, I didn't write it here. Okay, so let's also write it here. Two other identities. So sine squared equals 1 minus cosine squared. And also cosine squared equals 1 minus sine squared. So I'm also using these. So one more time. The negative sign with one sign and dx are all here within du. But let's see what we have left. We have a sine squared, which is 1 minus cosine squared, 1 minus u squared, and everything multiplied by cosine squared, which is our u squared. I will distribute negative in front, so we have u squared minus u to the 4th du, and we know the drill from here, u to the 3rd over 3 plus u to the 5th over 5 plus a constant c. So u to the u squared is u, the derivative of this is u squared. The derivative of this is u to the 4th, and of course I distributed a negative sign. Of course, as we always do, we replace u by the notation. So this is negative cosine to the 3rd x over 3, because it's an indefinite integral, plus cosine to the 5th divided by 5 plus a constant c. Okay, let's look at another example. Let's say 11, and that's on the same page, 498. In 11, we have the integral from, this is a definite integral, 0 to pi over 2, and we have sine squared times cosine squared dx. As we mentioned a minute ago, if sine and cosine have even powers, then I have to go back to reducing powers from sine squared to 1 minus cosine to twice x over 2, and respectively the cosine squared one. Okay, so let's see what we get then. 0 to pi over 2, this 1 minus cosine twice x over 2, and this is 1 plus cosine twice x over 2 dx. Okay, moving on. 2 times 2, I'll go outside. 1 minus a minus b times a plus b is 1 minus cosine squared twice x dx. As I mentioned before, cosine squared of 2x now changes into 1 plus cosine 4x divided by 2. So 1/4 outside, 1/4 times 1, the integral from 0 to pi over 2 dx, minus 1/4. I'm going to write it first so you can see it first, and then I'll replace it. 1/4, the integral from 0 to pi over 2 from cosine squared 2x dx. Now I will replace it. And I think I'm on page 3. Yes. So here is 1/4 x from 0 to pi over 2 minus 1/4 the integral from 0 to pi over 2 from 1 plus cosine 4x divided by 2 dx. So let's evaluate this. So 1/4 times pi over 2 is pi over 8. When I plug in 0, I'll get 0, minus 1/4 times 1/2, negative 1/8. The integral from 0 to pi over 2, and I have 1 plus cosine 4x dx, and this is pi over 8 minus 1 over 8, the integral from 0 to pi over 2, again from dx, minus 1 over 8, the integral from 0 to pi over 2 from cosine 4x dx, finally, pi over 8, again, minus 1 over 8x from 0 to pi over 2. And here I have negative 1 over 8. Sorry, I meant to write sign. Okay, I'll correct it. 4x, of course, divided by 4 from 0 to pi over 2. Let me correct it now so I don't forget, because I may scan it with the error in it. Okay, sin 4x over 4. Good. Where are we? So pi over 8 minus 1 over 8 times pi over 2. This is 1 over 32. And now carefully, 4 times pi over 2 is sine 2 pi, as we simplify to sine 2 pi. And then minus sine 0. But these are both 0. Sine 2 pi is 0. And sine 0 is 0. So all this term is 0. So then finally we have pi over 8 minus pi over 16. So this needs a 2 to pi minus pi is pi over 16. Getting more stuff out of the way. Okay. Good. I think we had enough examples of this, so let's go look at part 2, second half of this section. And I'm on page 4. And the second, so we had number 1, when we have integrals with powers of sine, cosine. And now we may have integrals, part 2, with tangent and secant. Integrals with tangent and secant, so powers of tangent secant. Okay, so what happens here is when tangent, if tangent has odd power, we should always think of, okay, let's go back here. So if I want, okay, so tangent squared plus 1 equals secant squared, of course. So if I need tangent squared, all I have to do is move 1 to the other side. So then I write tangent squared equals secant squared x minus 1. If secant has even power, secant has even, we should think of secant squared equals tangent squared plus 1. It depends on the problem. It depends on whether we need to use a substitution or not. Okay, so moving on, let's look at 21. And 21, I think, is on page 499. Yes, it is. And in 21, we have the integral from tangent x and secant to the third x dx. Okay, so let's take a look at this problem. And we notice that tangent has odd power. So I could be thinking of this just in case I need it. But look what happens if we simply realize that if we denote secant x by u, then du equals secant tangent dx. And what we have here is one of the secants, I'm borrowing one from here to our left. So secant tangent and dx will be the du. So what is left? A secant squared. So this is u squared du. Nothing else. One more time. Tangent secant dx, but I still have a secant squared, which is u squared. So this reduces to u to the third over 3 plus a constant c. So all I have to, rewrite secant cubed of x divided by 3 plus a constant c. Okay, that was an easy one. So let's look at 25. 25. Where are you, 25? Yes. So we have on the same page, 499. The integral from tangent to the fourth x secant to the sixth dx. Okay, so in this particular case, we are looking at secant, which has an even power. Tangent does not have an odd power. So we're looking at secant. So we are looking at this situation. So let's see what we can do here. Option 1. Well, I would simply replace or use a substitution u equals tangent x, in which I write du equals secant squared x dx. Let's see what is left in here. Okay, this is an easy one because I have u to the fourth. I borrowed 2 out of 6 for secant squared dx, but I still have power 4. I still have a secant to the fourth. But remember what we said, that secant squared is tangent squared plus 1. So this will be tangent squared plus 1, but everything squared because it's secant to the fourth. So let's see how we continue. Then jump over all this. Again, this is the integral from u to the fourth. 2 from the 6 secant to the sixth. 2 of them are borrowed for together with the x that make the du. And we have 4 of these left. 4, and I will replace secant to the fourth by u squared plus 1 squared. And then du. And from this moment on is just algebra to multiply the integral from u to the fourth plus 2u squared plus 1 du, more algebra, u to the eighth plus 2 u to the sixth plus u to the fourth and du. And finally, and then we will get back to the substitution. I think I'm on 5. Let me see how am I doing with time. Okay, that's good. Okay, so this is u to the 9th over 9 plus 2u to the 7th over 7 plus u to the 5th over 5, of course, plus a constant c. And now I have to go back to the substitution, which is tangent to the 9th plus 2 over 7, tangent to the 7th plus tangent to the 5th over 5 plus a constant c. Good. So that was 25. I think I'm going to stop here and continue with part B.